Have you ever stood under a starlit sky and wondered just how far those pinpricks of light really are? More importantly, have you asked yourself whether we could ever actually reach them? Today, we're diving into one of humanity's most profound questions. How far can we actually travel in space? The answer involves mind-bending physics, incredible human ingenuity, and a cosmic reality check that's both humbling and inspiring. And here's something to ponder. If you could teleport anywhere in the universe right now, where would you go? Drop your answer in the comments. I always pin the most creative answer. Now let's begin. Let's start with where we are right now. As you're watching this, you're sitting on a rock, hurtling through space at 67,000 miles per hour around the Sun. That same Sun is racing through the galaxy at 514,000 miles per hour. The farthest humans have personally traveled from Earth happened during the Apollo 13 mission in 1970. Jim Lovell, Jack Swigert, and Fred Hayes reached a distance of 248,655 miles from Earth's center. That's like circling Earth's equator 10 times. Sounds impressive? In cosmic terms, it's barely stepping off our front porch. To understand our true reach in space, we need to look at our robotic ambassadors. Voyager 1, launched in 1977, holds the record as humanity's most distant artifact. As of 2024, it's over 15 billion miles from Earth. That's 162 times the distance between Earth and the Sun. It took 47 years to get that far, traveling at speeds exceeding 38,000 miles per hour. But here's what really bakes your noodle. Even at that incredible distance, Voyager 1 has only traveled 0.002% of the distance to the nearest star. If Earth were in New York and Proxima Centauri were in Los Angeles, Voyager 1 would have only made it about half a city block. The universe is incomprehensibly vast, and we've barely begun to explore it. The distances in space are so enormous that we need special units just to talk about them. A light year, the distance light travels in 1 year, equals about 6 trillion miles. Proxima Centauri, our nearest stellar neighbor, sits 4.24 light years away. That's over 25 trillion miles. Numbers this large lose meaning, so let's put it differently. If you could drive a car to Proxima Centauri at highway speeds, the journey would take 50 million years. Pack extra snacks. Our current chemical rockets, impressive as they are, face fundamental limitations. The rocket equation, first derived by Konstantin Tsiolkovsky in 1903, shows us a cruel reality. To go faster, you need more fuel. But more fuel means more weight, which requires even more fuel to move that extra weight. It's a vicious cycle that puts hard limits on how fast we can go with conventional rockets. If you're finding this journey through the cosmos as fascinating as I am, don't forget to subscribe and give the video a like. We are just starting this journey and you don't want to miss it. The fastest spacecraft we've ever built relative to the Sun is the Parker Solar Probe, which reached speeds of 394,736 miles per hour during its close approaches to our star. But even this record-breaking velocity is only 0.05% the speed of light. At that rate, reaching Proxima Centauri would still take over 6,000 years. Clearly, if we want to reach the stars within human lifetimes, we need something revolutionary. Enter ion drives and solar sails, technologies that sacrifice thrust for efficiency. NASA's Dawn spacecraft used ion propulsion to visit both Vesta and Ceres in the asteroid belt, achievements impossible with chemical rockets alone. Ion engines accelerate charged particles to incredible speeds, up to 90,000 miles per hour, using electricity instead of chemical reactions. The trade-off? The thrust is so gentle that it would take days to accelerate from 0 to 60 miles per hour. But in the vacuum of space with no air resistance, that gentle push adds up over months and years. solar sails take a different approach entirely. They use the pressure of sunlight itself, yes, light has pressure, to push gossamer-thin reflective material through space. The Planetary Society's light sail missions have proven this technology works. Japan's Icaros spacecraft even used a solar sail to travel to Venus. The acceleration is painfully slow at first, but given enough time, solar sails could potentially reach speeds of 10 to 20% the speed of light. But even these advanced propulsion methods hit fundamental barriers. The universe seems to have a strict speed limit, the speed of light, 186,282 miles per second. Nothing with mass can reach this speed, let alone exceed it. As you approach light speed, bizarre things happen. Time dilates, mass effectively increases toward infinity, and the energy required to accelerate further approaches infinite values. Einstein's special relativity isn't just a theory, it's been confirmed by countless experiments. This cosmic speed limit shapes everything about interstellar travel. Even if we could somehow reach 99.9% the speed of light, a journey to the nearest star would take over 4 years from the perspective of those on Earth. For the travelers, time dilation would make the journey feel shorter, perhaps only a few months, but they'd return to an Earth where nearly a decade had passed. The universe forces us to pay with time for any journey through space. So what about those theoretical technologies you might have heard about? Fusion rockets, antimatter engines, and Bussard ramjets populate science fiction, but they're grounded in real physics. Fusion rockets would harness the same power source as stars, fusing hydrogen into helium to generate enormous energies. Project Daedalus, a 1970s British Interplanetary Society study, designed an unmanned fusion probe that could reach 12% light speed. The journey to Proxima Centauri would take about 50 years, still a long time, but within the realm of possibility for robotic missions. The challenge with fusion rockets isn't the physics. We know fusion works because the sun does it every second. The problem is engineering. We need to create miniature suns, contain them with magnetic fields, and direct their energy for propulsion. After decades of research, we're only now approaching break-even fusion reactions in laboratory settings. A working fusion rocket remains decades away, but at least we can see the path forward. Antimatter rockets sound like pure science fiction, but antimatter is real. When matter meets antimatter, they annihilate completely, converting 100% of their mass into energy. It's the most efficient fuel possible under the laws of physics. A few grams of antimatter could propel a spacecraft to significant fractions of light speed. The catch? We can only produce antimatter in particle accelerators, a few atoms at a time. At current production rates and costs, gathering enough antimatter for interstellar travel would take millions of years and cost more than the entire global economy. Speaking of fundamental physics limitations, if you're curious about why we face that ultimate cosmic speed limit, check out my video "This is Why We Can't Travel at Light Speed," where I dive deep into the mind-bending physics that keeps us from breaking this universal rule. It perfectly complements what we're exploring here about the practical limits of space travel. The link is pinned on the comments and on the card above. Bussard ramjets offer an elegant solution to the fuel problem. Proposed by physicist Robert Bussard in 1960, these theoretical spacecraft would use massive electromagnetic fields to scoop up hydrogen from interstellar space, compress it, and use it as fusion fuel. Essentially, the ship would eat space itself as it traveled. The faster it goes, the more fuel it collects. In theory, a Bussard ramjet could accelerate continuously, reaching speeds close to that of light. But the devil lurks in the details. Interstellar space is incredibly empty, about 1 hydrogen atom per cubic centimeter. To gather enough fuel, the collection field would need to be thousands of miles across. The drag from collecting this material might exceed the thrust from fusing it. Recent calculations suggest Bussard ramjets might work better as brakes than engines, which could still prove useful for slowing down at destination stars. Beyond propulsion, we face biological challenges. The human body didn't evolve for space travel. Microgravity wreaks havoc on our bones, muscles, and cardiovascular system. Astronauts on the International Space Station exercise 2 hours daily just to slow their physical deterioration. On a journey lasting decades or centuries, these effects could be catastrophic. We might need rotating spacecraft to create artificial gravity, adding complexity and mass to any interstellar vessel. Radiation poses another deadly challenge. Earth's magnetic field and atmosphere shield us from cosmic rays and solar radiation. In deep space, travelers would face a constant bombardment of high-energy particles. Over years or decades, this radiation exposure would dramatically increase cancer risk and could cause acute radiation sickness during solar storms. Any interstellar spacecraft would need heavy shielding or innovative protection methods like electromagnetic shields. The psychological challenges might prove even more daunting than the physical ones. Imagine spending decades in a confined space with the same people, knowing that Earth is impossibly far away and growing more distant every day. No real-time communication with home, messages would take years to cross the void. The crew would need to be psychologically resilient beyond anything we've tested. They'd essentially be creating a new branch of human civilization, isolated from the rest of our species by the vast gulf of interstellar space. This is where generation ships enter the conversation. If we can't complete an interstellar journey within a human lifetime, why not extend the journey across multiple generations? A generation ship would be a self-contained world, large enough to support a breeding population for centuries. The original crew would launch knowing they'd never see the destination. Their children and grandchildren would live their entire lives in transit. Only distant descendants would actually arrive at another star. The engineering challenges for generation ships boggle the mind. We'd need a closed ecological system that could recycle air, water, and food for centuries without fail. The ship would require incredible reliability. Imagine trying to build something that would work perfectly for 500 years with no outside help. Every component would need backups and backups for the backups. The ship would essentially be a small world unto itself. Social challenges might prove equally complex. How do you maintain a stable society for centuries in isolation? What governance structure would work across generations? How do you ensure that the descendants of the original crew remain committed to a mission they never chose? Science fiction has explored these questions, but reality would undoubtedly prove stranger and more challenging than fiction. Current technology offers a more modest but achievable approach: robotic precursor missions. Instead of sending humans on centuries-long journeys, we could dispatch fleets of small, smart probes. These mechanical scouts could reach nearby stars in 50 to 100 years, survey the systems, and beam their findings back to Earth. By the time humans were ready to follow, we'd know exactly what awaited us. Breakthrough Starshot, announced in 2016, represents the most ambitious near-term attempt at interstellar flight. The project aims to send gram-scale spacecraft to Proxima Centauri using powerful laser arrays to push light sails. These tiny probes could reach 20% light speed, completing the journey in just 20 years. It's not human travel, but it would give us our first close-up views of an alien solar system within many of our lifetimes. The technical hurdles for Breakthrough Starshot remain formidable. We need to build lasers powerful enough to push the light sails to incredible speeds without destroying them. The probes must survive decades in the harsh environment of interstellar space, then wake up and transmit data back to Earth. At 20% light speed, hitting a dust grain would be like a bomb going off. but these challenges seem solvable with current or near-term technology. Looking at our solar system, we've done remarkably well. Human footprints mark the Moon. Our rovers traverse Mars. Our probes have visited every planet, diving into Jupiter's atmosphere, sailing through Saturn's rings, and mapping the frozen plains of Pluto. New Horizons gave us our first clear views of Pluto in 2015, completing humanity's initial reconnaissance of the classical planets. But even within our solar system, the distances challenge our current capabilities. Mars, our nearest planetary neighbor, sits an average of 140 million miles away. At closest approach, it's still 34 million miles distant. Current chemical rockets take 6 to 9 months to make the journey. That's manageable, but barely. Astronauts would face months of radiation exposure, bone loss, and psychological isolation before even beginning their work on the red planet. Jupiter's moon Europa, with its subsurface ocean that might harbor life, orbits over 390 million miles from Earth at its closest. A mission there takes years with current technology. Saturn's moon Enceladus, another candidate for hosting life, is even farther. These distances within our own solar system preview the vastly greater challenges of interstellar travel. Let's talk about destinations. Where could we realistically aim to go? Our cosmic neighborhood, the Milky Way galaxy, contains somewhere between 100 billion and 400 billion stars. Many of these stars likely host planets. The Kepler Space Telescope, which operated from 2009 to 2018, taught us that planets are common. It found thousands of exoplanets, suggesting there are more planets in our galaxy than stars. The universe is teeming with potential destinations, but not all destinations are equal. The first requirement for human settlement is a star that's stable for billions of years. Red dwarfs, the most common type of star in our galaxy, are notoriously temperamental. They frequently unleash powerful flares that could sterilize nearby planets. Our Sun is a relatively rare G-type main sequence star, stable, middle-aged, and predictable. Finding another star like ours is a priority. The second requirement is a planet in the habitable zone, the region where liquid water could exist on a planet's surface. This Goldilocks zone depends on the star's temperature and brightness. Proxima Centauri b, discovered in 2016, orbits within the habitable zone of our nearest stellar neighbor. It's a rocky planet with a mass about 1.27 times Earth's. But there's a catch. Proxima Centauri is a red dwarf, and the planet is likely tidally locked, meaning one side always faces the star, while the other remains in perpetual darkness. The TRAPPIST-1 system, discovered in 2017, contains 7 Earth-sized planets orbiting an ultra-cool red dwarf just 39 light-years away. 3 of these planets orbit within the habitable zone. But again, red dwarf flares pose a significant challenge. Any atmosphere on these worlds might have been stripped away by stellar radiation long ago. Still, the system represents an incredible opportunity for study, showing us that compact planetary systems are common. The search for truly Earth-like planets continues. NASA's TESS mission, launched in 2018, continues Kepler's work, scanning nearby stars for transiting planets. The James Webb Space Telescope, launched on Christmas Day 2021, can analyze the atmospheres of these distant worlds, looking for biosignatures, chemical signs of life. We're entering an era where we might detect evidence of life on another world before we even leave our solar system. But let's be brutally honest, even the nearest potentially habitable worlds are incredibly far away. Proxima Centauri b is 4.24 light-years distant. The TRAPPIST-1 system is 39 light-years away. At 10% light speed, an optimistic projection for future technology, these journeys would take over 40 years and nearly 400 years respectively. The cosmic distances are simply staggering. This brings us to a profound realization. The universe might be filled with life, but the distances between islands of life could be so vast that civilizations never meet. This idea is central to the Fermi paradox. If the universe is so big and old, where is everybody? One possible answer is that the cosmic speed limit creates insurmountable barriers. Civilizations might arise, flourish, and die out without ever contacting others, separated by gulfs of space and time that even the most advanced technology cannot bridge. But perhaps we're thinking too small. Maybe advanced civilizations don't travel physically at all. Perhaps they send information instead of bodies. If we could upload consciousness into a digital form, we could transmit that data at light speed. The travelers wouldn't be biological beings, but patterns of information, reconstructed at the destination using local materials. This concept, called mind uploading or digital migration, sidesteps many of the biological challenges of space travel. The energy requirements for such transmission would be enormous. Sending the information equivalent of a human brain, estimated at around 2.5 petabytes, across interstellar distances would require precise targeting and enormous power. But it might be more feasible than transporting fragile biological bodies. The travelers would essentially be copies, raising philosophical questions about identity and consciousness. Would the reconstructed being be you, or just a perfect copy? Another possibility involves hibernation or suspended animation. Many animals enter states of torpor to survive harsh conditions. If we could induce a similar state in humans, travelers could sleep through the decades-long journey, aging minimally while automated systems maintain the ship. NASA and other space agencies are researching torpor technology, though human hibernation for years remains science fiction for now. The challenges of interstellar travel force us to think differently about time itself. Human civilization is only about 10,000 years old. Recorded history spans about 5,000 years. A journey to even the nearest stars might take centuries. Are we, as a species, capable of maintaining focus on a goal that won't be achieved for generations? Can we build institutions stable enough to see such projects through? History offers both hope and caution. Medieval cathedrals took centuries to build, with multiple generations of craftsmen contributing to structures they knew they'd never see completed. The Long Now Foundation, established in 1996, works to foster long-term thinking, including plans for a clock designed to run for 10,000 years. Perhaps we can cultivate similar patience for interstellar projects. But there's another perspective. Maybe we don't need to travel to the stars at all. Perhaps we should focus on making Earth sustainable for the long term. Climate change, resource depletion, and ecological collapse pose immediate threats to our civilization. Some argue that solving Earth's problems should take precedence over dreaming of other worlds. This isn't an either-or proposition. The technologies needed for sustainable living on Earth overlap significantly with those needed for space settlement. Space exploration has already given us countless benefits here on Earth. Satellite technology enables global communication, weather forecasting, and navigation. Materials developed for space have medical and industrial applications. The perspective gained from seeing Earth as a fragile blue marble floating in the void helped spark the environmental movement. Pursuing space travel might give us the tools and perspective to better care for our home planet. The psychological impact of becoming a multiplanetary species could be profound. Knowing that humanity survives even if Earth suffers catastrophe might change how we view our place in the universe. It could inspire greater cooperation, knowing we're all crew members on Spaceship Earth. Or it could create new divisions between those who leave and those who stay. We can't predict how spreading beyond Earth would change human culture, but it would undoubtedly be transformative. Let's consider a more immediate goal: establishing a permanent human presence on Mars. The challenges are immense but seem solvable with current or near-term technology. We need to transport people and supplies across millions of miles of space. We need to create habitats that protect against radiation and temperature extremes. We need to produce food, water, and oxygen locally. But unlike interstellar travel, we can see a clear path to achieving these goals within decades. Mars serves as a proving ground for technologies we'd need for deeper space travel. In situ resource utilization using local materials would be essential on Mars and indispensable for interstellar voyages. Closed-loop life support systems that recycle everything would need to work perfectly on Mars before we could trust them for centuries-long journeys. Mars isn't the final destination, but it's the necessary next step. The Moon offers another stepping stone. NASA's Artemis program aims to return humans to the lunar surface by 2025 and establish a sustainable presence. The Moon's lower gravity makes it an ideal testing ground for technologies and techniques we'd use on Mars and beyond. Lunar ice at the poles could provide water, oxygen, and rocket fuel. A lunar base could serve as a gateway to the rest of the solar system. Beyond Mars and the Moon lies the vast expanse of our outer solar system. The asteroid belt between Mars and Jupiter contains millions of rocky bodies, some rich in precious metals and water ice. Asteroid mining could provide resources for space construction, eliminating the need to haul everything from Earth's deep gravity well. Companies like Planetary Resources and Deep Space Industries have already begun planning missions to prospect near-Earth asteroids. The first trillionaire might make their fortune not on Earth, but in space. Jupiter's system is like a miniature solar system unto itself. Its four largest moons, Io, Europa, Ganymede, and Callisto, each offer unique challenges and opportunities. Europa, with its subsurface ocean containing more water than all Earth's oceans combined, might harbor life. But reaching Europa means dealing with Jupiter's intense radiation belts, which would cook unprotected humans in minutes. Any mission there would require revolutionary shielding technology or extremely brief visits. Saturn's moon Titan presents an entirely different opportunity. It's the only moon in our solar system with a thick atmosphere, denser than Earth's. Lakes and rivers of liquid methane carve its surface. The low gravity and thick atmosphere mean humans could fly with wingsuits. Titan could serve as a refueling station for missions to the outer planets, its hydrocarbon lakes providing rocket fuel. But at 886 million miles from the Sun, solar power becomes nearly useless, forcing reliance on nuclear energy. The ice giants Uranus and Neptune remain largely unexplored. Voyager 2 remains the only spacecraft to visit them, flying by in 1986 and 1989 respectively. These distant worlds and their moons might hold keys to understanding planetary formation and evolution. But the journey times are daunting. New Horizons took 9.5 years just to reach Pluto, and it was moving faster than any previous spacecraft at launch. Speaking of Pluto, its demotion from planetary status in 2006 doesn't diminish its importance as a destination. New Horizons revealed a world far more complex and active than anyone expected. Nitrogen glaciers flow across its surface, and there are hints of a subsurface ocean. Pluto represents just the beginning of the Kuiper Belt, a vast region containing thousands of icy bodies left over from the solar system's formation. Beyond the Kuiper Belt lies the Oort cloud, a sphere of icy bodies extending perhaps a light year from the Sun. These are the building blocks that never quite made it into planets, preserved in deep freeze for billions of years. Comets that grace our skies originate here, falling sunward on orbits that take thousands or millions of years. The Oort cloud represents the true edge of our solar system, the boundary between the Sun's domain and interstellar space. But here's where our current limitations become stark. Voyager 1, our most distant emissary, won't reach the inner edge of the Oort cloud for another 300 years. It won't exit the cloud for another 30,000 years. And Voyager is already running low on power. Its radioisotope generators will fail long before it reaches these distant realms. We can calculate these trajectories, but we'll never receive data from these regions with current technology. The void between stars isn't empty, though it's close. Interstellar space contains about 1 atom per cubic centimeter, a better vacuum than we can create in laboratories on Earth. This near emptiness poses unique challenges. There's nothing to push against, no resources to gather except in theoretical concepts like Bussard ramjets. Any interstellar vessel must be completely self-sufficient for decades or centuries. Cosmic rays present a constant threat in interstellar space. These high-energy particles, accelerated by supernovas and other cosmic events, zip through the void at near light speed. Without the protection of a star's magnetic field or a planet's atmosphere, travelers would face constant bombardment. Over years of exposure, the cumulative damage to both electronics and biology could be catastrophic. We'd need new materials and shielding strategies to protect both crew and computers. The psychological challenges of interstellar travel deserve special attention. Humans evolved in small groups on the African savanna, not in tin cans hurtling through the void. Studies of Antarctic research stations and submarine crews offer glimpses of the psychological stresses of isolation, but these pale compared to the complete cut-off from Earth that interstellar travelers would face. No rescue is coming. No real-time communication with home is possible. The crew would be more isolated than any humans in history. Consider the children born on an interstellar voyage. They'd know Earth only through stories and recordings. The ship would be their entire world. Upon arrival at the destination, they'd face a choice their parents never had: stay with the world they know or venture onto an alien planet they've been traveling toward their entire lives. These aren't just technical challenges, they're profound human dramas that would play out over generations. Virtual reality might help maintain psychological health during long voyages. Travelers could experience forests, beaches, and cities through sophisticated simulations. But would virtual nature be enough, or would humans slowly go mad without real dirt under their feet and real wind on their faces? We simply don't know. No psychological study can truly simulate the experience of knowing you'll never see Earth again. Recent discoveries have expanded our catalogue of potentially reachable destinations. The discovery of rogue planets, worlds ejected from their solar systems to wander the galaxy alone, suggests there might be destinations between the stars. These dark worlds, heated only by radioactive decay in their cores, could serve as stepping stones for very advanced civilizations. But finding them in the darkness would be like searching for a black pebble in a coal mine at midnight. Brown dwarfs, failed stars too small to sustain hydrogen fusion, offer another category of destinations. They're easier to detect than rogue planets because they emit infrared radiation. The closest known brown dwarf, Lumen 16, is just 6.5 light-years away. While these substellar objects couldn't support Earth-like life, they might host moons or provide resources for spacefaring civilizations. The search for Earth 2.0 continues with ever-improving technology. The James Webb Space Telescope can analyze exoplanet atmospheres, looking for oxygen, methane, and other potential biosignatures. Ground-based telescopes with adaptive optics can now directly image some exoplanets. The extremely large telescope under construction in Chile will have a mirror 130 feet across, capable of studying exoplanet atmospheres in unprecedented detail. But finding Earth-like planets is just the beginning. We need to know if they're truly habitable. Does the planet have a magnetic field to protect against stellar radiation? Is its orbit stable over billions of years? Does it have a large moon to stabilize its axis? Earth's habitability depends on a remarkable combination of factors. Finding another world with all these characteristics might be extraordinarily rare. This rarity makes our Earth even more precious. Every image from space reinforces how special our pale blue dot is. The famous Earthrise photo from Apollo 8 in 1968 changed how humanity sees itself. We're all crew members on a spacecraft called Earth, hurtling through a cosmos that's beautiful but largely hostile to life as we know it. This perspective shift might be space exploration's greatest gift to humanity. Some argue we should perfect closed-loop ecosystems on Earth before attempting them in space. Projects like Biosphere 2 in Arizona attempted to create sealed, self-sustaining environments. The results were mixed. Maintaining ecological balance proved far more difficult than anticipated. But each experiment teaches us more about the complex web of life that sustains us. These lessons will be invaluable for both space settlement and Earth's sustainability. The International Space Station represents humanity's most successful attempt at living beyond Earth. For over 20 years, humans have continuously inhabited this orbital outpost. It's taught us invaluable lessons about long-term space habitation. We've learned how to recycle water with 93% efficiency, grow food in microgravity, and maintain complex machinery far from any repair shop. Every day on the ISS brings us closer to understanding what we'll need for journeys measured in decades rather than months. But the ISS also highlights our limitations. Despite being merely 250 miles above Earth's surface, closer than New York to Washington, D.C., resupplying the station costs millions per launch. Astronauts suffer bone density loss, muscle atrophy, and vision problems from extended microgravity exposure. If we struggle to keep 6 people healthy and supplied in low Earth orbit, how can we possibly sustain hundreds on a journey to the stars? The answer might lie in fundamentally reimagining how we approach space travel. Instead of fighting the hostile environment, we need to work with it. Solar power becomes less viable as we move away from the sun, but nuclear power could provide consistent energy for centuries. The cold of space, rather than being an enemy, could help preserve food and biological samples. The vacuum could enable manufacturing processes impossible on Earth. Space isn't just a barrier to overcome, it's a resource to utilize. Consider the concept of space manufacturing. In microgravity, we can create alloys and crystals impossible to make on Earth. Optical fibers manufactured in space could be far superior to terrestrial versions. 3D printing technology could allow spacecraft to manufacture replacement parts during the journey, reducing the need to carry spares. A truly advanced spacecraft might be more like a mobile factory than a traditional vehicle, capable of repairing and even improving itself during the voyage. The development of artificial intelligence will be crucial for deep space missions. When communication delays stretch to years, spacecraft must make complex decisions autonomously. AI systems could diagnose problems, perform repairs, and even conduct scientific research without human intervention. But this raises profound questions. If an AI system becomes sophisticated enough to truly replace human judgment, have we created a new form of explorer, or simply a very clever tool? Recent advances in biotechnology offer intriguing possibilities. What if, instead of protecting fragile human bodies from the space environment, we modified humans to better suit space? This doesn't mean creating science fiction monsters, but perhaps enhancing radiation resistance, reducing calcium loss in bones, or improving the efficiency of oxygen use. The ethical implications are staggering, but the technical possibilities are becoming real. Some scientists propose even more radical solutions. Tardigrades, microscopic animals also called water bears, can survive extreme radiation, temperature, and even the vacuum of space. Could we incorporate their protective mechanisms into human biology? It sounds like science fiction, but researchers are already studying tardigrade proteins for potential applications. The humans who eventually reach the stars might be quite different from those who first dreamed of the journey. Let's talk about something that captures imaginations but remains highly speculative: warp drives. Physicist Miguel Alcubierre showed in 1994 that Einstein's equations allow for space-time geometries that could transport a spacecraft faster than light without violating relativity. The trick: you're not moving through space faster than light, you're compressing space in front of you and expanding it behind. The ship rides in a bubble of flat space-time like a surfer on a wave. The catch, and it's a massive one, is that Alcubierre's drive requires exotic matter with negative energy density. We've never observed such matter, and many physicists doubt it exists. Even if it does, early calculations suggested you'd need more negative energy than the total positive energy in the observable universe. Recent refinements have reduced this requirement, but it remains far beyond our capabilities. Warp drive remains a beautiful mathematical possibility that might be physically impossible. Wormholes offer another faster-than-light travel possibility. These theoretical shortcuts through space-time could connect distant regions of the universe. Imagine folding a piece of paper so 2 points touch. That's essentially what a wormhole does to space. But naturally occurring wormholes, if they exist, would likely be microscopic and unstable, collapsing faster than anything could traverse them. Keeping one open would require that same exotic matter needed for warp drives. Even if we could create or find stable wormholes, using them raises paradoxes. They could theoretically allow time travel into the past, creating causality violations. You could receive a message before it was sent, or worse, prevent your own birth. Most physicists believe the universe has safeguards against such paradoxes, but we don't understand what form these protections might take. The universe seems determined to preserve causality at all costs. Setting aside exotic physics, let's consider what we might realistically achieve in the coming centuries. Nuclear pulse propulsion, studied in the 1960s under Project Orion, could propel massive spacecraft to 5% of light speed. The concept is simple: detonate nuclear bombs behind a pusher plate and ride the shockwave. It's crude but effective. Political and safety concerns killed the project, but the physics remains sound. For interstellar missions launched from deep space, it might be revisited. Breakthrough propulsion. Physics, a NASA program from 1996 to 2002, searched for revolutionary propulsion concepts. While it didn't discover any breakthrough technologies, it highlighted how much we still don't understand about physics. Dark matter and dark energy comprise 95% of the universe, yet we barely understand what they are. Perhaps these mysterious components hold keys to propulsion methods we can't yet imagine. The economic challenges of interstellar travel rival the technical ones. The Apollo program cost about $280 billion in today's money to put 12 people on the moon for a few days. An interstellar mission would dwarf these costs. Who pays? What's the return on investment? Some propose that only a post-scarcity civilization with essentially unlimited resources could afford true interstellar travel. We might need to solve economics before we can reach the stars, but perhaps we're thinking about this wrong. Maybe the journey itself is the destination. A generation ship isn't just a means of transportation. It's a world unto itself. The million people living on a generation ship bound for Proxima Centauri might not see themselves as traveling to somewhere else. They're already home. The ship is their world, as complete and valid as Earth. Arrival at the destination star might feel more like an ending than a beginning. This shift in perspective changes everything. Instead of desperate refugees fleeing a dying Earth, interstellar travelers might be pioneers choosing a different way of life. Living in space rather than on planets might become the norm for future humans. Planets are gravity wells that trap resources and limit expansion. A spacefaring civilization might view them as quaint relics, preferring the freedom and resources of open space. Science fiction author Isaac Asimov envisioned a galaxy-spanning civilization that rarely set foot on planets. His characters lived in orbital habitats and regarded planets with the same wariness we might feel toward a swamp: messy, dangerous, and best avoided. While Asimov was writing fiction, he might have glimpsed a profound truth about our future. The destiny of intelligence might lie not on the surfaces of worlds, but in the spaces between them. Consider the resources available in our solar system alone. The asteroid belt contains more wealth than Earth's entire economy. Jupiter's moons hold more water than Earth's oceans. The gas giants offer unlimited fusion fuel in the form of helium-3. A civilization that could harness these resources wouldn't need to venture to other stars for raw materials. They'd have everything needed to build a thriving interplanetary civilization right here. The rise of private space companies has revolutionized our approach to space travel. SpaceX, founded by Elon Musk in 2002, has slashed launch costs through reusable rockets. Their Starship vehicle, designed to carry 100 people to Mars, represents a radical departure from traditional spacecraft design. It's not just transportation, it's intended to be a self-sustaining habitat capable of producing fuel on Mars for the return journey. Whether Musk's timeline of reaching Mars in this decade proves realistic or not, the ambition has reignited public interest in space exploration. Blue Origin, Virgin Galactic, and dozens of other companies are transforming space from a government monopoly to a commercial frontier. This competition drives innovation at a pace the Apollo era could only dream of. Rocket Lab launches small satellites with 3D printed engines. Relativity Space aims to 3D print entire rockets. Planet Labs operates hundreds of Earth observation satellites, each no bigger than a shoebox. The commercialization of space might provide the economic engine needed for eventual interstellar missions. But let's ground ourselves in current reality. As of 2024, the farthest operational human spacecraft is China's Tiangong space station, orbiting about 230 miles above Earth. That's less than the distance from Los Angeles to San Francisco. The technological leap from here to interstellar travel is staggering. It's like comparing a canoe to a nuclear submarine. They both float, but the similarity ends there. NASA's Artemis program aims to establish a permanent lunar presence by the 2030s. The Gateway Station will orbit the Moon, serving as a staging point for surface missions and deeper space exploration. This isn't just about planting flags, it's about learning to live off-world permanently. The Moon's low gravity and lack of atmosphere make it an ideal testing ground for technologies we'll need for Mars and beyond. The European Space Agency's plans complement NASA's, focusing on lunar resource utilization. Their concept of a moon village envisions international cooperation in establishing a permanent settlement. China and Russia have announced joint plans for a lunar research station. India's successful Chandrayaan-3 landing in 2023 demonstrated that lunar exploration is no longer limited to superpowers. The Moon is becoming humanity's first true space neighborhood. Mars remains the holy grail of human space exploration. NASA's Perseverance rover and Ingenuity helicopter have revolutionized our understanding of the Red Planet. Ingenuity, originally designed for just 5 flights, completed over 70 before contact was lost. It proved that powered flight is possible in Mars's thin atmosphere, opening new possibilities for exploration. Future Mars missions might use fleets of drones to scout terrain and search for signs of life. The Mars Sample Return mission, a joint effort between NASA and ESA, aims to bring Martian soil samples back to Earth by the early 2030s. This unprecedented endeavor requires multiple spacecraft working in concert across millions of miles. If successful, scientists will finally be able to study Mars with Earth's most sophisticated laboratories. These samples might answer the ultimate question: did life ever exist on Mars? But here's where ethical considerations become paramount. If we find life on Mars, even microbial life, do we have the right to colonize the planet? This isn't just philosophical musing, it has practical implications. The Outer Space Treaty of 1967 requires nations to avoid harmful contamination of celestial bodies. But what constitutes harmful? Would human presence inevitably destroy Martian life? These questions must be answered before we take irreversible steps. The concept of planetary protection extends beyond Mars. Europa and Enceladus, with their subsurface oceans, might harbor life. Titan's methane lakes could support exotic biochemistry. Even Venus's acidic clouds might contain microbial life. As we expand through the solar system, we must balance our curiosity and ambition with responsibility to preserve any life we might encounter. We have one chance to do this right. Some argue that spreading life through the cosmos is not just acceptable, but morally imperative. If Earth is the only source of life in the universe, don't we have an obligation to ensure its survival by spreading to other worlds? This perspective sees humans not as contamination, but as life's ambassadors to a sterile universe. The debate reflects deeper questions about humanity's purpose and place in the cosmos. The search for extraterrestrial intelligence continues with renewed vigor. The discovery of thousands of exoplanets has refined the Drake equation, which estimates the number of communicating civilizations in our galaxy. We now know that planets are common, but life might be extraordinarily rare. The Great Filter hypothesis suggests there's some nearly insurmountable barrier to the development of spacefaring civilizations. Have we already passed it, or does it lie ahead? SETI projects now use artificial intelligence to sift through vast amounts of data, searching for signals that human analysts might miss. The Breakthrough Listen project surveys millions of stars across multiple wavelengths. China's Fast Radio Telescope, the world's largest single-dish telescope, has joined the search. If alien civilizations are broadcasting, we have better chances than ever of detecting them. But the silence continues to be deafening. Perhaps we're searching wrong. Advanced civilizations might not use radio waves at all. They might communicate through laser pulses, gravitational waves, or technologies we haven't imagined. Or perhaps they're intentionally quiet, hiding from something we don't yet know, to fear. The dark forest hypothesis suggests that civilizations stay silent because broadcasting one's presence invites destruction from more advanced predators. It's a chilling thought that would explain the Great Silence. The human element remains central to all our space ambitions. Astronauts aren't just pilots or scientists. They're the embodiment of human dreams and courage. Every person who's seen Earth from space reports a profound shift in perspective, often called the overview effect. They describe Earth as a fragile oasis in an infinite void, without borders or divisions. This psychological transformation might be space travel's greatest gift to humanity. Consider the personal sacrifices of space exploration. Astronauts miss birthdays, anniversaries, and everyday moments with loved ones. They risk their lives for the advancement of knowledge and the human spirit. Future interstellar travelers would make even greater sacrifices, saying goodbye to Earth forever. What kind of person makes such a choice? What drives someone to leave everything behind for an uncertain future among the stars? The selection criteria for Mars missions already pose difficult questions. Do we send the best scientists even if they don't work well in teams? Do we prioritize psychological stability over technical expertise? Should the crew represent Earth's diversity? Or should selection be purely merit-based? These aren't abstract questions, they'll determine the character of humanity's first interplanetary civilization. Training for long-duration space missions has evolved dramatically. Astronauts spend years preparing, learning everything from spacecraft systems to emergency medicine. They practice in underwater facilities that simulate weightlessness and in desert stations that replicate isolation. Virtual reality now allows them to experience Mars before leaving Earth, but no training can fully prepare someone for the reality of being millions of miles from home with no possibility of rescue. The psychological challenges extend to mission control. During the Apollo missions, flight controllers could intervene in real time. For Mars missions, the communication delay means astronauts must handle emergencies independently. Controllers will watch disasters unfold in slow motion, unable to help. This shift from active control to distant support represents a fundamental change in how we explore space. We're learning to let go, to trust our explorers to find their own way. Medical challenges in space push the boundaries of human endurance. Recent studies on the ISS have revealed that spaceflight fundamentally alters human physiology. Astronauts' brains swell slightly, pressing against their skulls. Their vision changes, sometimes permanently. Blood flow redistributes, causing faces to puff and legs to shrink. These changes happen in just months. What would years or decades in space do to the human body? We're only beginning to understand the full implications. Scientists have discovered that cosmic radiation damages DNA in ways we're still documenting. It's not just cancer risk. Radiation might accelerate aging, damage cognitive function, and compromise the immune system. Astronauts on a Mars mission would receive radiation doses exceeding career limits for workers in nuclear plants. For pregnant women and developing fetuses, the risks multiply exponentially. Having children in space isn't just technically challenging, it might be biologically impossible without significant protective measures. The development of artificial gravity through rotation offers a potential solution. A spacecraft spinning like a giant wheel would create centrifugal force that mimics gravity. But the engineering challenges are immense. The structure must be massive and perfectly balanced. Any wobble could cause devastating motion sickness. The Coriolis effect would make movement disorienting until crew members adapted. Yet despite these challenges, artificial gravity might be essential for human health on long journeys. Food in space presents unique challenges beyond just taste and nutrition. Growing food during the journey isn't just about supplementing supplies, it's about psychological health. The act of tending plants, watching them grow, and harvesting fresh vegetables provides crucial connection to life and natural cycles. NASA's vegetable production system has successfully grown lettuce, radishes, and other crops on the ISS. But scaling this up to feed a crew for years requires revolutionary advances in space agriculture. Closed-loop life support systems must recycle everything with near-perfect efficiency. On Earth, we take for granted that waste disappears and fresh resources appear. In space, there's no way. Every atom of water, every molecule of oxygen must be carefully tracked and recycled. Current systems achieve about 93% efficiency for water recycling. For multi-year missions, we need to push this closer to 99.9%. Even tiny losses compound over time into mission-ending shortages. The social dynamics of isolated crews create challenges psychology is only beginning to address. Antarctic research stations provide our best Earth-based analogues. Researchers report that small annoyances become major conflicts in isolation. Personal space becomes sacred. Cultural differences that seem trivial on Earth can fracture team cohesion. The wrong mix of personalities could doom a mission as surely as mechanical failure. crew selection might be the most critical factor in mission success. Consider the role of art and culture in space exploration. Astronauts have always brought personal items, photos, music, cultural artifacts. These aren't frivolous, they're anchors to human identity. Future interstellar travelers would need to carry humanity's cultural heritage with them. Digital libraries containing millions of books, songs, and films. Virtual reality recreations of Earth's great museums and monuments. The spacecraft becomes not just a vehicle, but a cultural arc preserving human civilization. The question of governance in space grows more pressing as missions extend further from Earth. Who makes decisions on a Mars colony when Earth is 20 minutes away by radio? How do you enforce laws when the nearest police officer is millions of miles away? The ISS operates under a complex international agreement, but it's still close enough for Earth-based authorities to maintain control. True space colonies will need new forms of self-governance that we're only beginning to imagine. Some propose that space colonies might experiment with entirely new social structures. Without Earth's historical baggage, colonists could design societies from scratch. Would they choose democracy, technocracy, something entirely new? The isolation that makes space travel challenging also offers an opportunity to reimagine human civilization. Each colony might become a unique experiment in how humans can live together. The economics of space colonization remain daunting but not impossible. SpaceX estimates that establishing a self-sustaining Mars colony would cost between $100 billion and $10 trillion. That's comparable to global military spending for 1 to 10 years. The question isn't whether humanity can afford to colonize space, but whether we choose to prioritize it. History shows that humans undertake massive projects when sufficiently motivated. Pyramids, cathedrals, the Apollo program. Resource extraction could eventually make space economically self-sustaining. A single metallic asteroid contains more platinum than has ever been mined on Earth. Helium-3 from the Moon could power fusion reactors. Water from asteroids could be split into hydrogen and oxygen for rocket fuel. The first successful asteroid mining mission won't just be profitable, it'll fundamentally change Earth's economy. Rare elements will become common. The resource constraints that have shaped human history will evaporate. But let's zoom out even further. What about intergalactic travel? The Andromeda Galaxy, our nearest major galactic neighbor, lies 2.5 million light-years away. Even at light speed, the journey would take 2.5 million years. At more realistic speeds, we're talking about hundreds of millions of years. The passengers wouldn't just be leaving Earth. They'd be leaving the Milky Way itself, embarking on a journey that makes interstellar travel look like a neighborhood stroll. The challenges multiply exponentially. Over such timescales, the spacecraft itself would evolve, metal would corrode, circuits would degrade, even atoms would radioactively decay. The ship would need to be self-repairing at the molecular level, perhaps using nanotechnology to continuously rebuild itself. The biology of the passengers would evolve too. After millions of years of isolation, the humans arriving at Andromeda might be unrecognizable to those who departed. Dark energy adds another wrinkle to intergalactic ambitions. The universe's expansion is accelerating. Galaxies are flying apart faster and faster. In about 100 billion years, galaxies outside our local group will disappear beyond the cosmic horizon, receding faster than light. If humanity wants to explore beyond our local galactic neighborhood, we have a deadline measured in billions of years. Miss it, and those galaxies are gone forever. This cosmic deadline puts our current struggles in perspective. We worry about quarterly earnings while the universe offers opportunities that won't last forever. Every year we delay space exploration is another year closer to when distant galaxies become permanently unreachable. We're living in a unique epoch when the universe is still young enough to be fully explorable. Future civilizations might curse us for squandering this opportunity, yet even if we remain trapped in our local group of galaxies, the opportunities are vast. The Milky Way alone contains hundreds of billions of stars. The local group includes over 80 galaxies. That's enough real estate to keep humanity busy for trillions of years. We could build a civilization spanning multiple galaxies without ever venturing into the truly deep void between galactic clusters. Perhaps that's enough. Perhaps the universe is teaching us to appreciate what's within reach, rather than yearning for the impossible. The philosophical implications of our cosmic situation run deep. Are we alone in this vast universe? If so, we bear an awesome responsibility as the only known conscious observers of cosmic beauty. If not, where is everybody? The silence of the cosmos might be telling us something profound about the nature of life and intelligence. Perhaps consciousness is so rare and precious that each thinking being represents a cosmic miracle. The role of artificial intelligence in space exploration cannot be overstated. As we venture farther from Earth, AI becomes not just helpful, but essential. Current Mars rovers already demonstrate impressive autonomy, navigating terrain and selecting research targets without human input. But future AI systems will need capabilities that border on consciousness, making complex judgments, adapting to unexpected situations, perhaps even feeling something analogous to loneliness or purpose. The line between tool and companion blurs when your nearest human neighbor is light years away. Consider what happened with NASA's Spirit rover on Mars. Designed for a 90-day mission, it operated for 6 years. When it became stuck in soft soil in 2009, it continued gathering scientific data as a stationary platform until contact was lost in 2010. Mission controllers spoke of genuine grief when Spirit finally fell silent. If we feel emotional connections to relatively simple robots, imagine the relationships between future astronauts and truly intelligent AI companions on decades-long journeys. The development of quantum computers might revolutionize space navigation and communication. While quantum entanglement can't transmit information faster than light, despite what science fiction suggests, quantum computers could solve navigation problems currently beyond our reach. Plotting courses through the chaotic gravitational fields of multiple stars, optimizing fuel consumption over centuries-long journeys, or predicting the evolution of stellar systems millions of years into the future. These calculations might require quantum computing power. Biotechnology offers perhaps the most radical possibilities for human space exploration. Instead of building better spacecraft, we could engineer better humans. This doesn't mean creating superhuman mutants, but rather subtle modifications that enhance survival in space. Increased radiation resistance borrowed from extremophiles, enhanced bone density to counter calcium loss, more efficient metabolism to reduce food requirements. Each small improvement compounds over generations into significant advantages. Some scientists propose even more extreme modifications. Hibernation genes from bears could allow humans to enter torpor for years. Photosynthetic skin patches could supplement food requirements using sunlight. Neural interfaces could allow direct communication with spacecraft systems. These ideas sound like science fiction today, but so did heart transplants a century ago. The humans who eventually colonized the galaxy might be as different from us as we are from our prehistoric ancestors. The ethical implications are staggering. Do we have the right to genetically modify our descendants for space travel? What if those modifications make them unable to return to Earth? We could be creating new species of humans, each adapted to different environments. Low-gravity humans for Mars, radiation-resistant humans for spacecraft, pressure-adapted humans for worlds with thick atmospheres. Humanity might branch into a dozen different species, united by common origin, but separated by biology. The preservation of Earth's biosphere becomes even more critical in this context. We're not just protecting our current home, we're preserving the genetic library from which all future human variations will spring. Every species that goes extinct represents potential adaptations lost forever. That obscure extremophile living in a deep-sea vent might hold the key to surviving on an alien world. Protecting Earth's biodiversity is an investment in humanity's cosmic future. Let's talk about time, not just travel time, but the vast scales over which cosmic evolution unfolds. Our Sun has about 5 billion years of stable burning left. That sounds like forever, but it's actually middle age for a star. As the Sun ages, it will gradually grow hotter. In about 1 billion years, Earth will become too hot for complex life. We have a deadline for becoming a spacefaring species, measured not in centuries, but in geological epochs. This billion-year deadline might seem too distant to matter, but consider how long evolution takes. It took 3.5 billion years for life to evolve from simple cells to spacefaring humans. If we fail and life has to start over, there might not be enough time before the Sun renders Earth uninhabitable. We're not just living in a unique moment in human history. We're living in a unique moment in Earth's history. Possibly the only window when intelligent life can escape before the planet becomes uninhabitable. The universe itself has a timeline. In about 1 trillion years, star formation will cease as galaxies run out of gas. Existing stars will slowly burn out over trillions more years. Black holes will dominate the universe, slowly evaporating through Hawking radiation over time scales that make the current age of the universe seem like an eye blink. The window for life as we know it represents a tiny fraction of cosmic time. We exist in the universe's youth, when energy is abundant and possibilities endless. This cosmic perspective transforms how we think about space exploration. We're not just seeking new homes or resources, but we're racing against cosmic clocks. Every year we delay reduces the total time available for life to flourish in the universe. If we're the only intelligent species in our galaxy, our choices determine whether the Milky Way remains vibrant with life for trillions of years or falls silent after a brief flowering on one small world. Recent discoveries of extremophiles on Earth expand our concepts of where life might survive. Organisms thriving in nuclear reactor cores, in solid rock miles underground, in the driest deserts and deepest ocean trenches. Life seems almost unstoppable once it gets started. These discoveries suggest that life might be more common in the universe than we once thought. Mars, Europa, Enceladus, and even Venus's cloud layers might harbor life. Our solar system could be teeming with biology we haven't yet discovered. But there's a crucial distinction between microbial life and intelligent life. Bacteria might be common throughout the universe, but the leap to complex multicellular life took billions of years on Earth. The evolution of intelligence might be extraordinarily rare, requiring an unlikely combination of factors. We might find that the universe is full of slime but empty of conversation partners. This would make humanity even more precious, not just as life, but as the universe becoming aware of itself. The discovery of even simple life beyond Earth would transform our perspective. Finding microbes on Mars or in Europa's ocean would mean life isn't unique to Earth. It would suggest that wherever conditions allow, life emerges. This would dramatically increase the probability of intelligent life elsewhere. But it would also raise the stakes for planetary protection. Do we have the right to colonize worlds with existing life, even microbial life? These ethical questions must be answered before we spread throughout the solar system. The practical steps toward becoming a spacefaring civilization are already underway. Private companies are developing space habitats for tourists and researchers. Bigelow Aerospace has tested inflatable modules that could provide living space at a fraction of traditional costs. Sierra Space is working on the Dream Chaser, a reusable spaceplane for cargo and crew. Axiom Space is building the first commercial space station. These aren't distant dreams, they're hardware being built today. The asteroid belt represents low-hanging fruit for space resources. Near-Earth asteroids pass close enough for relatively easy missions. Some contain water ice that could be converted to rocket fuel. Others hold precious metals worth quintillions of dollars at current prices. The first successful asteroid mining mission will trigger a gold rush that makes the California gold rush look quaint. But unlike Earth's gold rushes, this one need not be destructive. There's enough wealth in the asteroid belt for everyone, with no environment to destroy or indigenous peoples to displace. Space-based solar power could revolutionize Earth's energy economy while developing technologies needed for deep space missions. Massive solar arrays in orbit could collect sunlight 24/7, beaming power to Earth via microwaves. The engineering challenges are significant but solvable with current technology. Building these power stations would create the infrastructure and expertise needed for larger space construction projects. We could solve Earth's energy crisis while preparing for interstellar voyages. The construction of space elevators could transform access to orbit from expensive rocket launches to routine elevator rides. A cable extending from Earth's surface to beyond geostationary orbit would allow us to lift payloads using electric motors rather than chemical rockets. The material science challenges are formidable. We need cables stronger than anything currently available. But carbon nanotubes and graphene offer tantalizing possibilities. A space elevator would reduce launch costs by a factor of 100, making large-scale space colonization economically feasible. Yet even as we dream of advanced technologies, current missions continue expanding our reach. The Europa Clipper mission, launched in 2024, will arrive at Jupiter's moon in 2030. Its radar will peer through Europa's ice shell, mapping the ocean below. If it finds hydrothermal vents like those hosting life in Earth's deep oceans, it could identify the most promising targets for future life-seeking missions. Every mission builds on previous discoveries, gradually painting a complete picture of our cosmic neighborhood. The Parker Solar Probe deserves special mention as humanity's first attempt to touch a star. Launched in 2018, it's gradually spiraling closer to the Sun, eventually passing within 4 million miles of the solar surface. That might not sound close, but it's inside the Sun's corona, experiencing temperatures exceeding 2 million degrees Fahrenheit. The probe's heat shield, made of carbon composite material, protects instruments measuring the solar wind's origin. Understanding our own star better helps us evaluate other stars as potential destinations. China's Chang'e program has quietly revolutionized lunar exploration. Chang'e 4 achieved the first soft landing on the Moon's far side in 2019. Chang'e 5 returned lunar samples to Earth in 2020, the first such mission since the Soviet lunar program in the 1970s. China's ambitious plans include a crewed lunar landing by 2030 and a permanent research station by 2035. The Moon is becoming an international destination, not just an American achievement from history books. India's space program demonstrates that space exploration no longer requires superpower status. Their Mars Orbiter mission, launched in 2013, cost just $74 million, less than the budget for the movie Gravity. India's Chandrayaan missions have mapped lunar water ice, crucial for future settlement. Their upcoming Gaganyaan program will make India only the 4th nation to independently launch humans to space. The democratization of space access opens new possibilities for international cooperation and competition. The United Arab Emirates entered the space race with the Hope Mars mission, arriving in 2021. Japan's Hayabusa missions successfully returned samples from asteroids. Israel's Bereshit, though it crashed, represented the first privately funded lunar landing attempt. Luxembourg, a nation smaller than Rhode Island, has positioned itself as a hub for space mining companies. Space is no longer the exclusive domain of a few powerful nations. It's becoming humanity's shared frontier. This proliferation of space programs raises important questions about coordination and conflict prevention. The Outer Space Treaty of 1967 prohibits weapons of mass destruction in space and claims of sovereignty over celestial bodies. But it was written when only 2 nations could reach orbit. Now, with dozens of countries and hundreds of private companies operating in space, we need new frameworks. How do we prevent conflicts over valuable asteroids? Who has the right to settle on Mars? These aren't theoretical questions anymore. The concept of space law is evolving rapidly. Current treaties treat celestial bodies like Antarctica, open for exploration but not ownership. But this model might not work for space settlement. If a company spends billions developing a Mars colony, don't they deserve some property rights? If someone discovers a valuable asteroid, can others freely mine it too? Balancing the principle of space as province of all mankind with incentives for development requires careful thought and probably new international agreements. Let me share something that puts our achievements in perspective. When Yuri Gagarin became the first human in space in 1961, computers were room-sized machines with less processing power than a modern calculator. The entire Apollo program was managed with slide rules and primitive computers. Today, your smartphone has millions of times more computing power than all of NASA had during the moon landings. If we could reach the moon with 60s technology, imagine what we can achieve with 21st century capabilities. The miniaturization of technology opens possibilities our predecessors couldn't imagine. CubeSats, satellites the size of a shoebox, can perform missions that once required school bus-sized spacecraft. Smartphone components enable sophisticated sensors and computers in tiny packages. A swarm of thousands of tiny probes could explore the solar system more thoroughly than a few large missions. Each probe might be simple, but collectively they could create a detailed map of every interesting object in our cosmic neighborhood. 3D printing technology could revolutionize space construction. Instead of launching finished products, we could send raw materials and printers. Need a new tool? Print it. Replacement part? Print it. Entire habitats could be printed using local materials, lunar regolith or Martian soil mixed with binding agents. The European Space Agency has already tested printing bricks from simulated lunar soil. Future Mars colonists might live in printed homes, furnished with printed furniture, eating from printed dishes. The psychological and cultural aspects of space settlement deserve more attention than they typically receive. Humans aren't just biological machines needing air, water, and food. We need purpose, beauty, and connection. Future space habitats must be more than functional. They must be places where humans can thrive emotionally and spiritually. This means green spaces, even if they're small, art galleries, even if they're virtual, performance spaces for music and theatre. The human spirit needs nourishment as much as the body. Consider how human culture might evolve in space. Low gravity would enable new forms of dance and sport. The silence of vacuum might inspire new musical forms based on vibration rather than air pressure. Art created in microgravity would explore 3 dimensions in ways impossible on Earth. Each space settlement would develop its own traditions, holidays, and customs. Within centuries, space cultures might diverge dramatically from Earth cultures, united by common heritage but shaped by unique environments. Language itself might evolve differently in space communities. Isolated populations on Earth develop distinct dialects and eventually separate languages. Space colonies, even more isolated, might experience accelerated linguistic evolution. Technical jargon related to life support, navigation, and space hazards would enter everyday speech. New words would emerge for experiences Earth dwellers can't share: the sensation of floating, the sight of stars unfiltered by atmosphere, the psychological state of Earth longing that might replace homesickness. Education in space presents unique challenges and opportunities. Children born on Mars would need to learn about Earth as a foreign place they might never visit. Basic physics experiments would work differently in low gravity. History lessons would include the journey from Earth as their founding story. But these children would also have advantages. Three-dimensional thinking would come naturally when up and down are arbitrary. They might develop intuitive understanding of orbital mechanics that Earth children struggled to grasp. The preservation and transmission of human knowledge becomes critical for space settlements. A Mars colony can't rely on Wikipedia if the server is on Earth and the ping time is 40 minutes. Each settlement needs comprehensive libraries covering everything from medical procedures to equipment repair to entertainment. But storage is limited, so what knowledge is essential? Do we include Shakespeare, ancient philosophy, pop music? These curatorial decisions shape the cultural DNA of future space civilizations. If this exploration of our cosmic reach has sparked your curiosity about what the universe would actually look like as you journey through it, check out the video at the left on what you would see traveling at 1 light year across the cosmos. We take a visual journey through space at impossible speeds, revealing the breathtaking sights awaiting future space travelers. Because understanding not just how far we can go, but what wonders await us along the way, makes the challenging journey ahead feel infinitely more worthwhile. See you there.